Hello everybody, this is Unit 1, Atomic Structure, Section 4, Electron Configuration. So you should have out in front of you a periodic table and a piece of paper because we don't have any guided notes for this, so you will be writing your notes on your own. Make sure you hit the key points and write down some of our explanations. We are going to add some stuff onto our periodic table, so make sure you have a good writing utensil, maybe some highlighters or something out as well. So the whole purpose of this section of notes is for us to identify what the arrangement of electrons is. We've talked about energy levels, we've talked about the fact that it's hard to pinpoint down where electrons are, but we can give a location for them, a general location for them, and that's what we're going to be doing today. So we need to have a quick reminder about what energy levels are. They're just the areas in an atom where electrons can exist, and the further out you go from the nucleus, the more energy an energy level has. So when we are filling electrons inside an atom and pinpointing their location, we actually start with the energy levels that are closest to the nucleus, so energy level number 1. And then we fill up as many of those as we can based off of how many electrons we have. Remember, we can only fit a certain number of electrons in each energy level. We add the electrons from the interior of the atom out. So from energy level 1, we fill up and we move out and out and out and out and out. If you take a look on your periodic table and you look at the periods, there should be 7 periods. Remember, the periods are horizontal rows. Now, that number 7 should look very familiar to you because I've also told you that there are 7 energy levels in an atom. Conveniently, the periodic table is arranged by where the electrons are at in an atom. So the next step to understanding where electrons are in an atom would be understanding what sublevels are. Remember, I told you that energy levels can be broken down into their sublevels, and sublevels are a shape. It's a shape region where the electrons can exist inside that energy level. And there's 4 possible sublevels: S, P, D, and F. And we've got S here on the left, and S is always this circle shape. It's just a sphere. It's pretty compact. Then we have this P shape, which looks like 2 dumbbells. And there's actually 3 different types of P's. And the reason why I know there's 3 different types of P's is because these sublevels can rotate. They can rotate around in order to fill the most space possible on an atom. Remember, the whole goal of electrons is to be as far apart from each other as possible. So the p orbital, if you look at that, that's just up and down right now. But I could rotate that and make it horizontal, and that fills up a different space on the atom. I can put those on top of each other so you guys can kind of see that. Why isn't it deleting? Here we go. Okay, so if I show you the different types of P's, there's one that goes up and down, and electrons can fit in there. And then I can have another one that's side to side, horizontal. I can even have one, and this one's going to be kind of hard to draw, that's going out towards you and going out behind you. See how each of those fills a different 3D space? Everywhere where there's an available space is going to be an available sublevel. And the rest of them are kind of hard to draw, so I'm not going to draw them. But there's SP, and then D has this quadruple dumbbell thing, and then F has this insane, like, crazy flower shape. But really all we're talking about here is different shapes where electrons can be, and these shapes are inside of the energy levels. So remember, each of those sublevels can actually be broken down. Those sublevels can be broken down into what we call orbitals. And I guess it's not actually breaking down a sublevel, but it's the different ways we can orient the sublevels to fill the shape. The S is just a circle, right? If I turn that sphere around, it's still going to be a sphere. It's still going to fill the same space. So there's only one type of S orbital. It's only one. And that S orbital always holds 2 electrons. The P, remember I had 3 different types of P. One that went up and down, one that went horizontal, and one that went like out towards us and into the back of the iPad that I'm holding, or into the back of the computer or whatever. There's 3 different ways I could orient that P to fill different spaces. So that's why I can have 3 different types of p orbitals, and each orbital can hold 2 electrons. So that gives me 6 total orbitals, or 6 total electrons inside the p orbital. So here I've got one S, one type of S, I've got 3 types of P. Each box is representing the 3 different P's. I can move around that d orbital, that really wonky shape, to fit 5 different spaces in the atom. So that's why we have 5 boxes for the d. And then I can do the same thing with the f orbital, but I can fill 7 different locations on the atom, and that's why I have 7 boxes for the f. So I can fit 14 electrons in F because 2 fit into each orbital, and I can have 7 different orbitals in the F sublevel. So I know this seems like a lot so far. We're going to make this a little bit easier coming up. But the first thing before we get there is how we can show where the electrons are. And one way to show where the electrons are is using something called an orbital diagram. And when we are creating an orbital diagram, we're doing these box things down here, where each box represents an orbital. Each coefficient here, if you look at the numbers down here, each coefficient represents your energy level. The SP, I guess it's just S and P here, but the S and P are the different sublevels, and each box is an orbital. The electrons here in red, these are your arrows. Your arrows are represent the electrons. So now we have electrons filling in the orbitals, which are corresponding to a sublevel, S, P, D, or F, and each of those are going into a specific energy level. So I'm really telling you where the electrons are inside an atom. So I'm going to get back to this exception thing in a second. But what you need to know when you're doing this is we're going to fill that lowest energy level first. So we're going to put electrons inside the first energy level, and then the second energy level, and then the third. And the other thing you want to notice is the arrows are pointing in different directions. And I want you to pause the video and actually think about why the arrows might be pointing in different directions, remembering that the arrows are representing electrons. So hopefully you paused the video and thought about that for a minute. And remember that electrons are all negatively charged. And electrons are trying to repel each other constantly. So that's one reason why we can only fit 2 electrons inside an orbital. It's because they're repelling each other. But the only way we can fit those 2 electrons in the orbital is by making them spin in opposite directions. So if I have 1 electron or 2 electrons like that, this electron might be spinning counterclockwise, or clockwise in that case, and this would be spinning counterclockwise. And this allows them to repel, but be in a similar space. But you see, I can't have them spin in any other direction, so that's why I can only fit 2 inside the orbital. We're going to practice drawing these in just a minute, but our rules so far are that we have to fill up energy level 1 first, we have to point the arrows in opposite directions, and then the last thing I want you to notice is in this 3p over here. Okay, in the 3p orbitals down there, we have the electrons going in separate boxes. Why do you think that might be? Pause and think about it. So it all comes back to the electron repulsion. I've got 3p orbitals there that exist, and if I have 3p orbitals in existence that are the same energy, they're in the same sublevel, p, then it's not really any different for an electron to be in the first orbital, the second orbital, the third orbital. But they want to be as far apart as possible, so we're going to fill each box first. If I had another electron, then I could double it up, like that. Or if I had another one, I would double it up, or I would double it up a third time. But you only do that when you have to. You want the electrons as spread apart as you possibly can get. So in order for us to figure out where exactly these electrons should be, what orbital, what energy level, all that jazz, we're going to use our periodic table as a tool. Now, your periodic table doesn't tell you exactly where the electrons are, but it is a fantastic tool for us to use to figure that out. So on your periodic table, remember that the energy levels are represented by your periods, period 1, 2, 3, 4, 5, 6, 7. Your sublevels, S, P, D, and F, are actually corresponded to what we call blocks on the periodic table. So you can actually label this on your periodic table right now, where the purple region here is your S block. And actually, I don't like that this is a different color, but this 1s over here, the helium, that should actually be purple because it belongs right there. Then we have our D block, which is in the middle. our P block on the far right and our F block down at the bottom. So we can use the periodic table to figure out what orbital the electrons are in. We can use the periodic table to figure out what energy level they're in. Then we can also use the periodic table to figure out how many electrons are inside each orbital or inside each sublevel. The number of electrons in that block, S, P, D, or F, correspond to the number of electrons that can fit into that sublevel. So if you look in the S block, there are 2 elements there in each period. 1, 2. So that means 2 electrons can fit into the S orbital. If you look at the P block, 1, 2, 3, 4, 5, 6, that's 6 elements there. That means that there can be 6 electrons inside that sublevel. Now remember, I said you could only fit 2 electrons per orbital, so 6 divided by 2, that means there are 3 p orbitals. So you actually don't need to memorize those numbers on the previous page. If you understand how to use your periodic table, then you'll understand how to make an orbital diagram, and then the next thing, which would be how to make an electron configuration. So an orbital diagram is a little more time consuming, whereas an electron configuration is kind of shorthand. And it uses coefficients, like the big numbers here. It uses letters, S, P, D, and F, and then it uses exponents to show what energy level, what sublevel, and how many electrons there are. And we use this thing called the electron configuration to show the arrangement of electrons inside an atom. So here are the rules for writing an electron configuration. I want you to pause, write down all of the rules. You need all of these. Don't just skip this step. Actually write them down. So rule number 1 is you need to figure out the number of electrons in an element. And remember, when we're talking about an atom, the number of protons, your atomic number, is the same as the number of electrons. So you really just need to look at the atomic number, the big whole number in your periodic table. And then we're going to write an electron configuration where we're writing down where every single electron is. And we fill from the first energy level. And inside the first energy level, it's small, so there's only enough room for an S sublevel. So we're going to fill the 1s area first. And remember, I can only have 2 electrons there. The coefficient is going to represent our energy level. I'm going to have a letter to represent my sublevel, and then I'm going to have electrons represented by an exponent. And I'm going to place each electron following along my periodic table, and at the very end, I should be able to add up the exponents, and that would be my number of electrons, which would represent the atomic number. So here's beryllium. Beryllium, if you look, has an atomic number of 4. You are going to get an electron configuration that looks like this. 1s2, 2s2. Remember, the coefficient represents our energy level. The letters represents our sublevels. And then the electrons are represented by our exponents. So before I even tell you how I got to this using a periodic table, I'm just going to double check that it's right. So remember, I told you that if you add up the exponents, 2 plus 2 equals 4, then that'll get you to the number of electrons you had in the element. So now let's talk about how we get here. So you're going to pull out your periodic table again, make sure you have that in front of you, and I'm going to put one on my page. Alright, so now you're going to put a finger on beryllium, Be. So beryllium is right here. Beryllium is in the second group, in the second period. So that means we're going to have, remember, energy level is represented by period. So we're going to have our last electrons in energy level number 2. Also notice that beryllium is in the S block. So that means our last electrons are going to belong in the S orbital. So I'm going to start off with energy level number 1. That's represented by period 1. I'm going to start counting the atoms here, or the electrons here. And the way I'm going to count the electrons is using the atomic numbers of our elements. So atomic number 1, that is in energy level number 1. That is in block S. And I have 2 electrons there. We move helium over to the S block and just pretend it's over in the S block. Now there's nothing else in energy level number 1. So I'm going to move over to energy level number 2 now. So 2, we're still in the S block, and I'm going to count 2 electrons, and now we have 1s2. Pretty simple, right? So if I was going to do my orbital diagram, then I would be drawing, delete all this stuff. Okay, so for my orbital diagram, I'm going to have two S blocks, 1s, 2s, and now I'm going to fill in my electrons. 1, 2, remember we start off with the lowest energy level first, we have 2 electrons in there, and then our 2 electrons in the 2s block. That is my orbital diagram for my electron configuration, which was 1s2, 2s2. You might be asked to do either of these pieces of information. So now we're on sulfur, and sulfur is 16 electrons, so we're going to do the same thing for sulfur. So I'm going to pull up my periodic table, and while I'm doing that, you should point your finger on sulfur. Alright, so sulfur is way over here in the P block in energy level number 3. So that means our last electrons are going to be in the 3p sublevel. But we need to start way over here at hydrogen. You can't just skip all the way to 3p whatever sulfur is. You have to start at the beginning, and I need to know where each electron is. So this is going to be kind of long. The answer is right above you, so you can see that. So I have 1, energy level number 1, S block, 2 electrons. There's nowhere else to go. So now I have to go to energy level number 2. S block, 2 electrons. Going to go all the way across. Now we're at the 2p block. So 2, because energy level number 2 still. P orbital, 1, 2, 3, 4, 5, 6. 6 electrons there. Nowhere else to go, so we're going to go to energy level number 3. 3s2, all the way over to the 3p, and we have 1, 2, 3, 4. 3p, 4. So that's our electron configuration for sulfur, and I'm going to go ahead and I'm going to start drawing the orbital diagram as well. So for the orbital diagram, I'm going to start off with the 1s, and I have 2 electrons spinning in opposite directions. Then I have the 2s with 2 electrons spinning in the opposite directions. And then I have the 2p. Now remember, I can only fit 2 electrons in each orbital, so if I have 6 electrons, that must mean that I have 3 orbitals. And you fill them all up first, and then you start doubling them up. Okay, now we've got our 3s, up, down, and then we have our 3p. Remember, p has 3 orbitals, but this time I only have 4 electrons, so 1, 2, 3. They have to be separate first, and then 4 doubles up before moving up to the next energy level. So I'm going to do one more. I'm only going to do the electron configuration for this one, but I want you guys to do the electron configuration for vanadium. So if you take a look back, go back to where we had the exceptions on the orbital diagram page, and I want you guys to pause and try and figure this out on your own first. So hopefully you gave yourself a shot. You should have started at the 1s. So 1s2, 1, 2. Then we move down to the 2s2. Move all the way across to the 2p. 1, 2, 3, 4, 5, 6. Nowhere to go, so I go down to 3. 3s2. Nowhere to go, so go across. 3p, so we're still in the 3rd energy level. 1, 2, 3, 4, 5, 6. 6 electrons there. Now we're at the energy level number 4. So we're at 4s2. Now remember the exceptions page said we always fill 4s before we fill 3d. But there's no d orbitals in the 3rd energy level. There's no d orbitals right here. But what actually happens is this guy here, we consider that to be 3d. The yttrium here would be considered to be 4d, and it's kind of obnoxious, but your periodic table helps you out, and it already has it so that we would, if we're following the rules going from left to right, we would fill 4s first, and then we get 3d, 1, 2, 3. 3d, 3. So that's the electron configuration for vanadium. We might ask you to draw electron configurations all the way down to barium, but I'm not going to ask anything further than that, because if you look on your periodic table, the F, this guy, the lanthanum, actually fits right in between barium and hafnium, and actinium fits right in between radium and rutherfordium. And when we fill up the F orbitals, it actually gets really wonky. So I'm not going to require you to fill them up on the test or even do a whole lot of examples with them. Just know that we can, and that it exists, and that electrons can fill there, but that some weird stuff sometimes happens. But at this point, you should feel comfortable doing an electron configuration and making an orbital diagram for any element all the way up through barium. We are going to do some practice in class next time, but I recommend if you're confused, write yourself a note for exactly what you are confused on. What does the coefficient represent? How did you know to go to this orbital at this instance? Give me actual questions to answer rather than just saying, I don't get it or I don't know. Because I can't help you if you just tell me, I don't understand. If you tell me where I lost you or where you misunderstood, then that can actually help us and we can get somewhere with that.